which is electronics. So we're going to go through and have a look at all of the things that you need to build all of the electronics in order to do NMR. That we need to do NMR. So we will have a look at what each of the things does, why we need it, and then all of the things that you need to actually use. So we want to make these pulse sequences. We've got some software on the computer, but there is all of the stuff that goes in the gap in between. These are the minimum number of things that you need to achieve NMR. Some of these are expensive, some of these are cheap, but you need to have all of them. They are color-coded on there. Everything that is in pink is kind of halfway between transmit and receive. Green is what we would call the set of components that we use for transmitting, and the blue ones are the things that we will use for receiving our signals. So we start at the very top and we work our way down through the green stuff and then back through the blue stuff, which is where we measure our signals. There are a million different ways that you can do this, but at the kind of fundamental level, you always need something that does the job of each of these components. So going through each one from the beginning, the first thing we need is a system that can generate the frequencies that we saw yesterday. So we're looking at something that can do 1, 2, 3, 4, 5, 10, 20 megahertz. You can use something like a signal generator. You can have very small, very cheap systems that do it all on a little chip and will output the signals that you need. We just need something that will make a sine wave or a square wave or some kind of signal that is at the frequency that we need. We then need to take that sinusoidal signal and send it to lots of different places. So to do that, we use a thing called a splitter. A splitter splits the signal. None of these are complicated. The splitter splits the signal, but it does it in such a way that if you stick something on here that is badly matched in impedance, like we saw yesterday, it doesn't affect the other one. If you just stick one wire and split it into different places, we will change the input to that system based on how badly matched it is elsewhere. So this prevents that happening. And as you get to higher frequencies, you can literally do it with some cleverly laid out copper on a board, or gold in this case. At lower frequencies, there's a little bit more going on inside that just makes it a little bit easier. But this is a block that you can just buy. They're not very expensive. Don't be sorry. We've literally just started. They're just a little block that you can buy, tiny box with some connectors on, and you just plug it in. But this is the job that it's doing. This is a new component. This is a diode. And diodes have these really weird behavior in that if you put voltage through it in one direction, it will flow really easily, and it will very, very quickly deliver you a full load of current, which you can see here. And this is 0.7 volts for silicon ones, 0.3 for germanium, and you can get different voltages depending on what you want to do. So, you are sending the synthesized signal to two places. It's coming into the phase-sensitive detector or demixer, which we'll look at in a bit, and it's going into the switch. If your phase-sensitive detector is not really well matched to everything else, you won't have really strong signals for transmitting. If your transmission switch is not very good, and often it's not very good, you will screw up the signal that's going to the phase-sensitive detector. You can do it. So one of the ways that we do it is to ditch that and have that all on one block. So you can have like a signal generator with 2 or 3 outputs. There's one way to do it. The cheapest way to do it is to have one synthesizer and then split the signal with the splitter. Yeah, good question. So the diodes are very strange, but the diodes give us something which is very useful, which is the ability to control whether a voltage does or doesn't flow based on how big it is. Okay, so when we're trying to transmit, all we are wanting to use is the big voltage. If the voltage is small, it's going to be noise. When we're trying to receive, we've got a very small voltage, and anything big is something that we don't want. So by changing where we put the diodes, you can control whether or not we do or don't get those voltages through. So at the minute we're noise limiting, which is when we're doing the transmit, I'm going to have a diode. I'm actually going to have two diodes, one forwards and one backwards. And everything in this middle bit is not going to go through. So we won't get any voltage appear at the other side until we reach this VF. So as long as our noise is smaller than 0.3 or 0.7, all we're going to get through is the big signal. Does that sort of make sense? We have one forwards and one backwards because we've got an oscillating signal. So when it comes up, it will be limited by one forwards, and when it goes down, it will be limited by the one that's backwards. So these come as a little crossed pair of diodes. Is everyone happy with that? Okay. The pulse programmer is basically a switch. I want to turn on and off our sine wave to make the pulses that we need to tip our spins into the XY plane. It can be as simple as an electronic switch. It just needs to either allow the signal through or not allow the signal through. And the pulse programmer will then basically turn that switch on or off. You can spend a lot of money on these, and you can buy a box that does all of this as a pulse programmer, frequency synthesizer, and all of the rest as a box. Or you can literally use an electronic switch like a transistor, small cheap board that generates signals and some diodes, and you will get pretty much the same outcome. So this need not be very expensive, but you can spend a lot of money on it. So that will take our on and off pulses from our pulse programmer. It takes our split signal from the frequency synthesizer, and it outputs our RF pulses, which we're trying to get. We need to set the widths of these appropriately, or the heights of these appropriately, to give us the right integrals that we need to tip our magnetization. If you have a very simple switch, we can only control that integral by changing the width, which is what you do on the spin core. So the 90 and the 180 are twice the width of each other rather than twice the amplitude. On the Gruning consoles, on the pure devices, I think you control amplitude instead, but that's slightly more complicated than just a transistor because you need something which can control the height of those pulses too. This is the correct direction. At the moment, we have very small signals. You maybe have 2 or 3 volts at max, and that is not really enough to do NMR effectively. Your pulses will be so painfully long that you'll get very few signals. So we need to take our very small signal, which we have, we put it into a power amplifier, and our pulses become very big. The bigger your amplifier, the shorter your pulses, the shorter the pulses, the easier and more likely it is that you're going to get signal. So you can do this with something like 5 watts of amplifier, which is not a lot. It's less than most speaker systems, but your pulses will be quite long. We normally use amplifiers that are 25 or 50 watts, and that gives you pulse durations which are a bit more friendly. On the bigger system, so the bigger your system is, the stronger the amplifier needs to be, because you need to deliver that field in a bigger area. So the MRI scanner is 1,000 watts or 1,500 watts. So you have these different levels depending on what it is that you need to actually achieve.
I'm sorry.
Please.
I mean short pulses again.
Yes, absolutely. So I think we will do it properly later, but the duration of the pulse determines the bandwidth of the pulse.
Mm-hmm.
So if you want to excite spins over a wider range of frequencies, you can do that by having a very short pulse.
Mm-hmm.
The longer the pulse is, the less spins of different frequencies you will excite. So if you've got a really good magnet, it doesn't really matter. So on the MRI, our pulses are something like 5 or 6 milliseconds. As the magnet gets worse and you get more and more bandwidth, or more and more signals, over a different frequency range, you need shorter and shorter pulses to get the signal. So for most of our systems that we have, we use 3, 4, 5 microsecond pulses, and then you actually get some signal. A 5 millisecond pulse on what we'll build later will have absolutely no signal. Yeah, really good question. This is the #1 reason NMR goes bad in our experience, and is one of the most important parts of the system. A, because it will help you get good NMR, and B, because it stops you breaking things. So we maybe have, let's say, 50 watts of power coming out of here. This wants to see your preamplifier something like a milliwatt of power. If you connect the 50 watts of that into this, you literally have fire, which is very bad, particularly as these are very expensive. So we need a thing which stops this going to this, and it can be extremely simple or it can be extremely expensive, depending on how well you want to do it. So the thing that allows us to do that is a duplexer. Okay, so the preamplifier does not like the loud noise of the big amplifier. The duplexer prevents that happening. It can be as simple, again, as another switch, but we tend not to use the electronic switches so much at low field, because they introduce a lot of noise of their own, which you don't suffer with if your SNR is good. So we'll have a look at some ways that we can do that in a bit. That then goes into the preamplifier. If you're very lucky, your signal at the moment might look like this. It's probably not quite that close to a sine wave. It just looks like noise, but we need it to be bigger noise. And we use a preamplifier for that. This is one of the things that is worth spending a bit more money on. We use a variety of different devices. If you are good with electronics, you can build your own for something like £80. Or you can buy little modules that are okay for sort of £100. If you want the best NMR, there are some very nice preamplifiers with very low noise that are more like £1,000, but they will give you really, really good NMR. The 3 things that you care about for the preamplifier is #1, it wants to have what we call a very high gain. So you want to take a very small signal in and get a very big signal out, and that is the gain. So how much you multiply in, you multiply it by the gain, that gives you out. The second is we want it to not bring lots of its own noise, and that's something called noise figure. And that will tell you how much extra noise it will add. Preamplifiers will always add noise. There is nothing you can do to get rid of it, but the amount of money that you spend is almost directly proportional to how much noise you will get at the output. If the signal that you have going in is very noisy and you add another load of noise, you will have no NMR. So we see it often with the worst of the probes that we build. If we use the cheap preamplifiers, we get no NMR. If you switch to the expensive preamplifier, you get good NMR. The third thing that matters is, just like we saw yesterday, again, the impedance match. So you can buy them matched to different impedances, and it needs to just be the same as everything else that you've got for maximum transfer. Everyone happy with this so far? Any questions? This is very ugly. Who can make it slightly prettier by putting it through a filter? These do not need to cost a lot of money. You can build your own. So just like the resonators that we saw yesterday, you can make your own filters out of capacitors and inductors. These kind of mini circuits ones are very good. They're tens of pounds, and you pick them depending on the frequency that you're working at. There are 4 types of filter. Low pass, which will get rid of anything above a certain frequency. High pass, which will get rid of anything below a certain frequency. Band pass, which lets through stuff over a little range in the middle. And band stop, which rejects a little bit in the middle. We almost never use band stop in NMR because there's not much that you want to get rid of at a specific frequency. if there is a band pass filter available for your NMR frequency, it is worth however much it costs to have the band pass filter, because it gets rid of everything that is not NMR. Most of the time, we don't work at a frequency that you can buy band pass filters for, because they're only really for things where you need them commercially. So 10 megahertz is a really good frequency to work at, because walkie-talkies have an intermediate frequency at 10 megahertz. So band pass filters for 10 megahertz are really easy to come by. Everything else doesn't really have them until you get to high frequencies. Then we tend to use a low pass filter, because most of the noise that we're going to pick up from the environment is a higher frequency than we're looking at.
Can you say the last one again?
Yes. So let's say we're working at 5 megahertz. We will normally have a 7 and a bit megahertz low pass filter. Pretty much all of the noise in the environment will be higher frequency than low frequency NMR. So the low pass is better than the high pass. You can connect high pass and a low pass to make your own band pass. But most of the time the low pass is good enough. If you can do it without a filter, and particularly if the system is good, you can do it without a filter. But often when we don't see NMR, sticking a filter in will make NMR appear, particularly if you're somewhere that's noisy electrically.
And if I'm working on the low field, let's say, I need to use the high field filters.
We will almost always go for low pass filters. So if you can't get it, there it comes. So if you think of frequency spectra, can you see on the camera? Is this okay?
Yes.
Very good. I'll try and stay this side. So if you think of this as a frequency spectrum of the noise in the environment, if you're down here with your NMR, let's say 5 megahertz, there will always be noise at 10 megahertz from people with radio transmitters. There will always be a load of noise which starts at sort of 90 megahertz from commercial radio, so radio stations. That gets extremely noisy from sort of 90 upwards. So trying to do NMR at 100 megahertz needs a lot of filtering, or to put it in a Faraday cage room. And there's some other kind of bits in between that are not too bad. The filters look like this. So they will let through stuff that's here, but not stuff that's here. So your low pass will let through everything below whatever the cutoff frequency is. High pass will let through anything above. But by the time you're down here, almost all of the noise is up here anyway. So pretty much if you're going to pick one filter, the low pass is always better. What you shouldn't do for 5 megahertz NMR is necessarily buy a 5 megahertz filter, because they define the frequency that they work at this point rather than this point. So if you have a 5 megahertz filter and put a 5 megahertz signal into it, you will only get half of the amplitude out. So you're always better to just go up a little bit. Mini circuits, who we use for a lot of the components, sell a huge, great range of filters, but there are not many choices down here. So you can have things like 5, 7.5, 10 and a bit, 15, 20, 1, don't know. And then they go 30, 50, 100. But as long as you're cutting out some of this, it's good. That's all right. This one makes our lives very easy if you don't have a lot of money. The signal which we are going to get from our NMR coil is going to come out at the NMR frequency, the Lamore frequency. If you are trying to collect directly a signal which is 5 megahertz, you need to spend quite a lot of money on the thing that converts it into digital data for the computer. The second thing is if you have anything other than perfect NMR coming out of the coil, even with the filter, your signal is still going to look like this, because you're going to collect everything that's coming around where you are, and that's still quite a lot of signal. So there is a component which has far too many names. They're called mixers, they're called phase-sensitive detectors. And it has a symbol which looks like this, and it does something extremely magical. If you put in a signal like this on the left, which is quite dirty and contains a lot of noise and is very, very small, and I put in here a signal which is perfectly at the Lamore frequency from our splitter, I will end up with very pretty NMR signals coming out the end. So the way that you can think of these as working is perhaps easier if the signal that you put in here is actually just a square wave. So the simplest phase-sensitive detector is basically a switch. And if I turn this on and off at the frequency of my NMR, I will only get ups and downs and ups and downs if that is happening at the exact same frequency as I'm turning the switch on and off at. The further away I get from turning it on and off at the right frequency, the less of that signal I will get through. Except what we're really doing here is multiplying this by this, okay? And if you multiply this by this, it's like when you tune a guitar and you get the kind of weird noise as you're almost tuned, is the difference between those two frequencies. If you have built your own console from scratch and you have control over every component, you can put this in at the exact same frequency as came out, and that's the best thing to do. So if you use the splitter, this will literally be the signal that has created this signal, and therefore you will come out just with the change in the amplitude of that. If you have not quite done that, so let's say you've got some bits of console from elsewhere that's doing generation, we will normally have this very slightly off the frequency, and you end up with these kind of wiggly echoes coming out. So those of you that have, you definitely see it on the spin core, but for those of you that have looked at tuning systems where you get an FID and you try and stop the FID being wiggly and try and get it so that it's smooth, it's adjusting this for this component. So if you are not perfectly on resonance, you will get a wiggle, and the frequency of the wiggle is proportional to the difference between this and this. So if you measure that frequency on an FID, you know how far off you are, and it's how the auto tune works. And then you can get it so that it's perfectly on resonance. If you do not spend a lot of money on everything else, this drifts around a bit, and you're actually better to set this slightly off, because then you don't see the drifting. And as long as it's less than 500 hertz, a kilohertz off between those, even with really cheap hardware, you can still collect the signal. This is extremely helpful, number one, because it allows us to get data out, which is easy to capture because it changes very slowly. The second reason it's very nice is it only lets through things which are very close to this frequency, and it gives you another stage of filtering. It is possible to do NMR without this. And you can, if you've got quite strong NMR, you will actually see on an oscilloscope an echo that is at 5 megahertz, as long as it's not very noisy. But this makes life so much easier, and they are tens of pounds, so it's not worth not having. Almost all commercial systems still do this as how they detect it. Whether or not they use one of these on its own, or whether or not they have it built into the main controller that does everything in the commercial systems, somewhere in there, either as code or as a real thing, there is a phase-sensitive detector or mixer. Is everyone happy with that? Does anyone have any questions about that? I couldn't see whether or not it was a thumbs up or a hand. Okay, so that's our animation to demonstrate the issue that you have with phase. So when you look at the panel where you set all of the different parameters, you will almost always have something called receiver phase or something like that. Receiver phase is a thing which shifts basically left and right this sine wave with respect to what's happening in there. And if we shift this very slightly to the right, we will suddenly lose most of our signal, because instead of turning it on when it's going up and turning it off and then turning it on when it's going down, we're now turning it on when this is off and turning it off when it's on. That's why we have receiver phase. The alternative is to not do that at all and to use two of these, which are 90 degrees out of phase. And then you guarantee that one of these will be capturing the signal. You can then do some easy maths with those to combine the two signals together, or you can use them to adjust the receiver phase again. Most of the systems, particularly if you're going to do stuff with FIDs, will adjust that phase somewhere, but we probably still capture it. This does not add enough to the cost to not have both. And we call that quadrature demixing, because it is a quarter of the way round out of phase. Okay. If you are completely in phase, you will have all of your signal in this one, and you will have pretty much nothing in that one. And then as you slide these, if we add 5 degrees to this, so 5 degrees and 95 degrees, we will start to shift into the other channel, but you will always have something in one of those channels. The maths that we use to combine those is basically to measure the whole of the length of the vector. And it's easiest if you treat it as a complex number. So that's why you will see real and imaginary on the channel names, because it's easy for the maths. It doesn't really mean anything other than two components which are 90 degrees out of phase, which real and imaginary are. You can then do everything with that and work out moduluses. You can dephase, rephase, and all of these things. So that's where we get real and imaginary from. Everyone happy with that? Okay, we have almost worked our way all of the way around the loop, and we are back to the middle. You need something now which will convert the data that is coming from all of that into something which you can see. The simplest way to do that is an oscilloscope. It's not very good if you want to record the data, but if you're building a system, it's always easiest to have an oscilloscope there and actually look at what is coming out. And you can poke it at different points throughout the system and you can really see what's going on. Here you can see FID signal on there, very clean, very nicely produced with a little bit of a wiggle. So we're perfectly on resonance with our phase sensitive detector there. And then you can look at the envelope of that, which would be when it was perfectly adjusted, or by taking the data and playing with it after. These are not very good if you want to make measurements of stuff, but when you're building a system, this is by far the best way to make sure that it's working, because you can actually see what's going on. And it's much easier to see why it's not working with an oscilloscope than trying to digitize the data. If you have got it down to very, very smooth, so if this is what your final signal looks like, you can even use a microcontroller to collect that. If it's a bit more wiggly, if you've got quite a high frequency, you would want some kind of analog to digital converter that plugs into the PC, or something more advanced, digital signal processing chip or something. Everyone happy with that so far? Okay. Yes, please.
How can you understand it's not working very well? What will we see then?
That's an excellent question, which is probably a day's long lecture in itself. The main things that we look for, so let's just fly all of the way back to the beginning. The places where this goes wrong is mostly here, because you're not generating the correct signals to do NMR. So we will always start, even if when we're building it, we will build this bit first and measure what's coming out of here and make sure it's correct. By the time you get past the power amplifier, it gets difficult to measure, because you can't just plug a power amplifier into an oscilloscope, because the oscilloscope doesn't like it. You can buy high voltage probes which you can stick into oscilloscopes if you're not sure about the power amplifier's workingness. But we will always start here and make sure that's looking correct. And the things that we're looking for are the pulses the duration they're meant to be? Are they the amplitude they're meant to be? Are they the spacing that they're meant to be? And all of these things. So we're checking that that's right. The next place where it tends to go wrong is here. And something has not worked here, which means that either this stuff is getting through. And so sometimes you will see, like on the, going back to the spin core again, but it takes a little while for the amplifier to actually turn off. And if you try and do NMR before it's turned off, all you're going to measure is a load of RF from the power amp. So we'll look then for that. Then we'll work our way around one block at a time. And what tends to happen is if you just set everything running and you adjust it so that you're in a position where you know you're going to get an echo, which is not straightforward in itself. So if you think about our pulse sequence, let's say we've got something like this. This is twice this, you'll have to pretend. And our echo is in the middle of that. This is maybe 200 or 300 microseconds. And the width of our echo might only be 1 or 2 microseconds. So you need to find a 1 microsecond thing in the middle of a 300 microsecond window, which means you will not be able to see this and this at the same time. If you have the oscilloscope, you can move it around and you'll sometimes get the echo in the wrong place because actually this isn't what you thought it was. Often there are some nuances about where the echo time is really defined from, especially if you've got duration rather than amplitude pulses. Tau is technically from the middle of the pulse to the middle of the pulse, but it might be that the pulse programmer didn't understand that the middle of the pulse was where you define these things, and so actually tau is, I don't know, 102 microseconds instead of 100 microseconds, and then that puts another 2 microseconds in there, and that's not where you were looking. So it gives you that freedom to play with stuff. The first time you get an echo on an oscilloscope, the chances are it looks like this. Amongst a load of other stuff that looks like this. But then you can tweak stuff around and you can change the phases and you can move the phase sensitive detectors and change the filters and these sort of things. And you will slowly get towards the point where you're getting echoes that look more like echoes. And those are the main things that we use to see where it's gone wrong. Okay, so we're going to have a look now at the duplexer and the simplest duplexer, which unfortunately means return to impedance matching and transmission lines. If you just have a wire, the stuff that comes out of the end is the same as the stuff that goes in the beginning, and whatever you do to one end happens to the other end. Weird things happen when your cable are multiples of quarters of a wavelength. Okay, so if you have a frequency of 5 megahertz and we work out the equivalent wavelength of 5 megahertz, so V is F lambda, and we divide the speed of sound, speed of light 3 times 10 to the 8 by 5 times 10 to the 6, you will work out the wavelength of 5 megahertz in air. Electrons travel more slowly than that in a cable. So we have something called a correction factor or velocity factor, which is normally 66%. So you divide that number or multiply it by 0.66, and that will tell you the wavelength of your frequency in a cable. If your cable are multiples of quarters of that, weird stuff happens, and it can only be described as weird stuff. But some of the weird stuff is useful to us. If you have 2 lots of a quarter, i.e. a half, or whole lots of that, you have whatever you stick on the end's impedance at the beginning. So we buy these with characteristic impedance, so we use everything at 50 ohms. if I have a 50 ohm cable, but I stick something on that's 5 ohms, I will see 5 ohms at the front. This is not particularly useful to us most of the time. The one that's useful to us is a quarter wave. And everything just goes really weird when you have a cable that is a quarter of the wavelength of that frequency in your cable. So once more back to the spin core. On the back of the spin core is a piece of cable which says quarter wave on it, and it is this. The weird things that happen are, if I connect the two ends here, so this is a coaxial cable, so there's a connector in the middle and a connector on the outside. If I connect those two ends together on a normal wire, I will short out whatever's at the beginning and it will really dislike it. With a quarter wave, if I short it out, it sees it as nothing connected. The opposite is also true. If I do not connect either end at the end, it thinks I've connected both of those connectors together at the beginning and it doesn't like it. But the thing which is useful to us is if you have then something here, which is the same impedance as the cable at a quarter wave, absolutely nothing is reflected whatsoever, and you have complete, pure, perfect transmission. We are going to utilize the fact that I can short out this end without upsetting what's at this end to make a duplexer. Okay, so if we go back to our duplexer picture, and I just have a switch which we're going to use for diodes down here, so I can just short this out when the signal that comes is too loud. This is going to be really cross because I've just connected both ends together, and it's like if you short across any electrical system, it sparks and stuff gets unhappy. So this is bad news, and it will see all of that power coming back to the power amplifier, and you will almost certainly break it. If, however, I now stick a quarter length cable in here and I short this end out, it just thinks I've left the end open and it doesn't care. Okay, that means that for the cost of 2 diodes, which are maybe a penny each, and a bit of cable, which is maybe 5 pennies, I have prevented this thing from destroying this thing, or this thing from destroying this thing. And it is as simple as that. This is the simplest duplexer. You can stick the numbers into a calculator online, you pick the type of cable that you've got, you pick the frequency that you're working at, and it will tell you how long to cut the cable. And you can prevent all of the damage to everything. The picture on here is of 2 diodes. We normally use 10 pairs of diodes because the more diodes you have, the more likely they are to deal with the fact that you're hitting them with a huge current from there. And you can do this as many times as you like, which I maybe have a picture of. I do not have a picture of. So you can do that one after another, after another, after another. And each time you do it, you will reduce a bit more the amount of signal that goes through. The first time I do this, if you remember right from the beginning of the diodes, these will allow through either 0.7 or 0.3 volts. The first time I do this, I will still be having 0.7 or 0.3 volts coming through, which is not too bad. It doesn't mind, but you will see it still in the signal. If I do this again, I'm now starting with a signal that's 0.7, and I might be able to lose a little bit more and a little bit more and a little bit more. One section is okay. The more sections you have, the shorter the dead time, which is the time between transmitting a pulse and being able to receive again. Okay. Does that make some amount of sense? So on the spin core, this is inside the box. This is inside the box. And there's a connector here and a connector here, and you just stick the bit of wire in the back. You can make the equivalent to this out of capacitors and inductors again. So the reason that we use this coax cable and it has this characteristic impedance is because it's like a load of inductors and capacitors connected together. You can build this same thing without a massive length of cable, just by using those components, but it gets a bit more complicated and a bit more involved. There was something else that I was going to say about that. The reason you might want to do that is because as you go down in frequency, you go up in the length of cable. By the time you are at 5 megahertz, you are just under a meter, just under a meter of cable. If you were to then go to 2.5 megahertz, you've got 2 meters of cable. And all of a sudden you have these massive, great long bits of cable that you're trying to A, deal with, and B, lose signal over. So the longer the cable is, the less signal you will have. They are perfectly practical down to 2 or 3 megahertz. They start to become a little bit less enjoyable by the time you get less than a megahertz. Then you sort of need to get a proper one. These are things that you can buy, but they are pretty much things that you can buy from Leonid or from the other companies that make NMR kit. They're not something you can just buy from any of the shop, and they only work over a narrow range of frequencies. You can abuse them outside that range of frequencies, which is exactly what we're going to do this afternoon, because the lowest frequency duplexer we have is 10 megahertz, and we will still get NMR at 5 megahertz, but you start to really, really suffer. And a lot of the time they will have the preamp built in too. Okay, does anyone have any questions about any of that stuff? Okay, so as we talked about yesterday, this is the complete set of things that you need to be able to do NMR without needing to build anything. Okay, so these are all things that you can just go online and order, and you will be able to do NMR. I've picked a signal generator because it's more in the spirit of buying things that will just work when you get them. They don't need to be programmed. You just type 10 megahertz, 5 volts in the front, and it will make 10 megahertz at 5 volts. A reasonable signal generator. So the problem is very cheap signal generators won't generate you megahertz of signal, and they won't generate it in a way that's stable enough that you can use it. So your minimum entry price for a reasonable signal generator is probably about £300 new. But there are plenty of second-hand signal generators. So you can pick up a really good £300 signal generator for £50. Okay. That then goes into our splitter, and most of these things are going to be from Mini Circuits because their stuff is very good, it's very reasonably priced, and they pretty much ship everywhere as long as you promise not to build missiles with it. This first one then is our splitter, which last Friday was £80. It has 3 connectors. One of them is in, 2 of them are out, or the other way around. You can have 2 in and 1 out, but that's not what we want. One of those will then go to our phase sensitive detector over there. Our other one will come to our switch. Our switch is same price, so £80. Mini Circuits like things that are $79.99. Into our switch, which has 3 connectors. One of them is the signal in, one of them is the signal out, and one of them is whether it should be turned on or turned off. Okay. I've picked a Teensy because we like the Teensies. They run really quick. They do need to be programmed on a computer. They're at the moment about £30, but you can use anything that can output pulses. You can buy a pulse generator box for the table, whatever you want. Included on here, but not included up before, is an attenuator, which is electrically controlled, and that will allow us to do a 90 and a 180 that look like this. If you can keep your 90 and the 180 the same duration, coming back to what we were saying about bandwidth, you will have the same bandwidth for both pulses. So we'll see in the next session why that's useful. But if you can afford the extra £96 and can do amplitude control instead of duration control, everything gets a lot simpler. So this one is quick enough that it can change between the amplitudes from the 90 to the 180. And there again, it just has some connectors in, and you pick high or low, and then in and out. Next is the power amplifier. The smallest power amplifier I would recommend to buy is 10 watts. You can do NMR at 1 watt, but it is very painful spending the money by a 10-watt power amplifier. It needs not be particularly good. There are loads and loads of power amplifiers available for people that use the ham radio, we call it. I don't know if it's called ham radio everywhere, but people that use like the citizen band transmission to speak to each other on radio. And one of the bands of that is 3 megahertz to 30 megahertz, which covers pretty much everything that we can build in the lab. So you can pick these up for next to no money. A 10-watt one on AliExpress is something like £20, and they just kind of work. They're quite dirty, they're quite noisy, but they will amplify your signals enough that you can do NMR. This is my personal favorite, which is made by a company in America called Henry Radio. The reason I like it is because you can whisper very gently electrically into it and have huge pulses come out of the end. These ones need quite a big push on this side and need therefore a more expensive signal generator. This and this together should cost about the same amount of money. If you spend lots of money on that, you can do this cheaply. If you have a cheap one of them, this will cost more. Henry Radio is a guy who makes this stuff. Shipping time is long, but they really are lovely, and they come in boxes, which I like. They're about £500, but they are really, really good. Then we have our first pair of cross diodes to get rid of the noise. They're less than £1. We then have our tuning and matching board from yesterday. The ones which we'll use this afternoon, the capacitors come to about £5. If you want to do the best job, there are capacitors, variable capacitors made by Johansson, which are quite expensive, or made by Voltronics, which are extremely expensive, but give you a really wide range of values and are really easily adjustable and very sensitive, which are like £150 of capacitor then. RF coil is a bit of wire. We've got a connector to connect then to our quarter wave and our next set of diodes. That then is going to go into our preamplifier. If you do not wish to build your own preamplifier, which I would highly recommend, the mini circuits do these little demo modules for the chips that they sell. The TB series of those come in different gains. This one, 8A plus, is about £150 and works really quite well. If you have the money, it's worth spending it and buying a really nice preamplifier. So the Mytech one, this AU1114, is about £500, I think, at the moment. The prices of those go really up and down. It's very strange. Then we have a filter. If you're building your own, it's like £1 worth of stuff. If you're going to buy one from Mini Circuits, either a BBP, which is the band pass, BLP is the low pass, they're about £60. Then we have our phase sensitive detector, 3 connectors, the NMR signal, the one to demix it by, and your output, about £80, and then into the oscilloscope. If you add up all of the numbers, it comes to about £1,000. If you buy the cheap stuff, if you buy the expensive stuff, it comes to about £5,000. If you buy a commercial system, they start at £15,000. So you're still making a massive saving, even if you're buying the expensive stuff. The reason this is better than buying a commercial system is, number one, it's £1,000 and not 15. The second reason is you will gain the best appreciation of what is actually happening with your NMR experiment if you have done this. I encourage everyone at some point in their lives to do this. A, because you should suffer like we have suffered, and B, because it really does, it really helps with your understanding, I think. Does anyone have any questions about that? Okay. So the question is, are we too early for coffeeing if we're early for coffee? And then it will make, then we can be early for lunch. Does that work?
We can go now and we can start that.
Perfect. Very good. Oh, I forgot to say that. I've put on the chat for the Zoom meeting a set of instructions that I cannot test because I do not own a Mac, but which should allow you from start to finish to install FEM. I cannot test these instructions because I do not have a Mac, but I went through all of the tutorials for all of the different steps, and I believe these are comprehensive enough that it should work. If this does not work, you will just have to use them on a PC, but it might be worth a go and just see if they work. Okay, last one. The last things to do is the pulse sequences that we use and how we test the instruments. We'll just do one last little recap on NMR and particularly relaxation. Then we're going to have a look at the pulse sequences that we use when we've built cheap things. And then finally, pretty much how we set parameters on a CPMG sequence. No. Yes. Okay, so we've seen yesterday about tipping our spins from aligned with the big magnetic field into the XY plane. And we just left it there and it processed around quite happily, and we didn't do anything about relaxation. There are two types of relaxation which we see in NMR and some subtypes of those. The first is longitudinal relaxation, which we often call T1. It is called longitudinal relaxation because it is about things going on the longitudinal axis, which is Z, or where B0 is. We have put a bit of energy, not a lot, into our system. We have tipped the spins. It needs to go somewhere, and it just goes to other stuff. So there is lots of stuff around the protons that we have excited. There are the things they are connected to. So in our water, that will just be an oxygen molecule. But there are other things around in bigger structures that they will also lose energy to. In physics, we call that a lattice. And so we sometimes call this spin lattice relaxation, longitudinal relaxation, or T1 relaxation, because it happens with this rate constant of T1. This is the formula for that relaxation, and you will have perhaps not necessarily seen it in this form. Maybe you have, I'm not entirely sure. But basically, there are not very many things going on. This is the maximum possible signal that you can have, and this is how many things that you polarize to start with. This is the time at which you're taking your measurement, and this is the rate constant or time constant T1. This bit often doesn't appear when you're looking at T1 plots, but is the bit that you need if you've gone to anything other than 90 degrees. So if you start with a pulse smaller than 90 degrees, this accounts for the fact that you didn't start at 90 degrees. You've gone past 90 degrees, it gives you the little bit extra that's below. So for most things that we do on cheap magnets, we ditch this bit and you get the formula that looks more like what you've probably seen for a T1 curve. This is a T1 curve. This is one where we've ditched the end bit and we've started from 0. So we're measuring how much magnetization there is along Z. If we've tipped at 90 degrees, there is none, and then it will build back up, back to equilibrium, and you can get no more signal than all of it along Z. Okay, so however many more of these we do, it will still be 1. Okay. If we look at this graph, so this is for a T1 of 1 second. In order to get back up to equilibrium, we need to wait at least 5 lots of T1. Okay, if you wait less than 5 lots of T1, we're going to start with less magnetization along our Z-axis. The consequence of that is you have to wait if you want to do more than one average. So if you think about measuring water, which has a T1 of something like 3 seconds, if you wait less than 15 seconds, before you do your next experiment, you do not have all of your signal, okay? We can use that to our advantage later, but for now it's just a pain and you need to wait long times before you can repeat your experiment.
So is there any way that we are using wrong repetition time?
Yes.
For measurement?
There are many ways we're using the wrong repetition time for the experiment. If you set your repetition time too long, your NMR will not suffer. You will suffer, but your NMR will be fine, okay? If you set your repetition time too short, you start to lose signal from things that have long T1s.
So getting 3 seconds, we are starting getting 2 seconds kind of.
Yeah, so let's take this one.
Okay.
So let's say, for example, we set our repetition time as 1 second. So I do one experiment and I get a load of signal because we've started from nothing. My next experiment is going to start with 63% of the signal. My next experiment starts with 63% of that signal. My next experiment is 63% of that signal. And after about 8 repetitions, I have no signal. Fortunately, it doesn't quite work like that, because each time we do it, we're going to tip them around. And actually, by the time you've made it all of the way around a circle again, life is okay. But you start to seriously lose the signal if you are right down this end of the curve. If you're up here, you will probably never notice. So technically, you need an infinitely long repetition time to make sure you've recovered all of your magnetization, but this is not how it works. So 7 T1s is 99.999 something percent of your magnetization. 5 is 99 and a bit, 99 and a half. If you use 3 T1s, you don't have to wait too long, and you're still most of the way back up. I was going to do setting parameters at the end, but whilst we're on T1, we may as well set T1. If you do not know T1 of your sample, measure T1 of your sample, and then you can set a perfectly optimized T1 that will give you the quickest experiment you can do without losing any signal. If you cannot be bothered to measure T1, you can set it long and reduce it until you start to lose the signal and just use that as T1, and that gives you a very quick guess at what it is. You can even use that as a way to estimate T1 at the point at which you start to lose signal. You are probably at 3, 4, or 5 T1s. Okay, so that's the easiest way to set the repetition time on an experiment. The thing to be careful of with repetition time is, let's say you've got a sample which is interesting and has different T1s inside it. If you have lots and lots of a short T1 and not very much of a long T1, and you get greedy with setting a short repetition time, you will get rid of the signal from the long T1, which is what we do. And it's a good way to get rid of signals. But if your intention is not to get rid of the signal, you will lose, maybe you've only got 5% of it in there, you will not be able to see it. In which case, then you need to really measure it and see what's going on. Yeah. Okay, so this is T1 curves for different relaxation times now. So this one is 2 seconds, and you see by 7 seconds, we've not got to our 5 T1, so it's not got all the way back, but our half a second has. Okay, transverse relaxation is wrong on many levels. T2 is not a relaxation at all. To be relaxation for physicists, energy has to go somewhere, and no energy goes anywhere in T2 relaxation. But it's like T1 relaxation, so that's its name. If you think right back to our first session, we have balls and sticks are magnets, and if you spin a magnet near another magnet, the magnets get cross. The same happens in our samples. If all of our spins are processing around perfectly in phase with each other, there will be no T2. But at the point at which they're near each other, and at the point at which they're truly processing, they will all interfere with each other a little bit. Not a lot, because they are very tiny magnets. That means on a local level, every single spin has a slightly different precessional frequency. This is why chemical shift spectroscopy, high field NMR stuff works. and you can measure those individual frequencies of individual protons, and it will tell you what they're attached to. In low field relaxometry, it's just about how much they're kind of interfering with each other. And that's why it's not in the presentation, but we've seen a couple of times the graph of T2 and T1 as a function of the sizes of molecules. That is because things that are very small and can get near each other and interfere with each other a lot will relax much more quickly than stuff that are big and far apart. If you have spins and they're near each other and they interfere, eventually they will start to get scrambled and they will all point in random directions and we will have no signal. This is T2. T2 is a property of your sample and is not something which can be measured by humans on Earth. You can only measure T2 star with an experiment. So T2 star, come back to you. T2 star is what you are measuring on this FID. So the envelope of this FID is T2 star, and T2 star is T2 because of your sample, plus a little bit less T2 because actually you've got different samples in there and this one is really different to this one and they're interfering with each other more. And the fact that this bit of magnet is a different frequency to this bit of magnet and this bit of magnet, and that is the thing that you are measuring. If you have an infinitely homogeneous magnet, if you have an infinitely homogeneous sample, you can measure T2. These do not exist. You are always going to measure T2 star. The better your magnet, the closer T2 star is to T2. The more homogeneous your sample is, the closer T2 star is to T2. But it's not a thing that you can measure directly. So this is the equation for T2 decay. It looks remarkably similar to the one for T1 decay, but it's the other way up. So our signals are being lost because we're measuring how much is in the XY plane. This FID is not quite on resonance. So going back to our phase sensitive detector, they're very slightly different and it gives us the wiggle in the spectrum. The problem with T2 star is it's incredibly dependent on how homogeneous everything is. And if you build a bad magnet, which is not homogeneous, T2 star is something like 1, 2, 5, 10 microseconds. The speed with which you can go from transmitting a repulse to receiving your pulse is something like 10, 20, 30, 100 microseconds, which means on pretty much all cheap magnets, we cannot get an FID. The FID is there, but it is already decayed by the time we can even turn on the receiver. This makes it fun when we bring our cheap magnets and stick them on your nice magnet consoles, because it wants to do an FID to tune it and it wants to measure these signals and they're not there. So this is the biggest problem with not poorly constructed magnets, but magnets that are not constructed and optimized to give you really homogeneous fields. That doesn't matter. It just means we need to do something different to get our signals. In our inhomogeneous field, one pulse does not give us any signal. We cannot do a one pulse experiment. You cannot do a 90 and get signal. We can build Halbachs relatively inexpensively that you can do an FID on. We can build geometries like we looked at yesterday that can do an FID, but they need a bit more time than just sticking some magnets in and hoping for the best. Fortunately, we've only been doing our experiment for something like 50 microseconds. So we've still got lots of T1. There's still lots of spins in the XY plane. So this is the solution to all of our problems. This is Han, who was a radar engineer and applied all of the things he knew about radar to NMR. And fortunately, other than ending up with some strange names for things, it has solved everything that we use in cheap, inexpensive systems. So we do a thing called refocusing, and we can basically make all of our things spin in the other direction. So if they were processing this way to start with and they all end up out of phase, I can refocus them and they will all spin back in the other direction. If you think about, maybe we have a movie, let's just watch a movie. If you think about what, go on. if you think about what this means for us, is after we've tipped our spins into the XY plane, if ones have processed very quickly and we get them to process very quickly backwards, they should take that same amount of time to all come back together. Our fast ones should go just as fast backwards. Our slow ones should go just as slowly backwards. And they should all come together at the same moment. And that generates what we call an echo, not because it's an echo, but because that's what it's called in radar. We can see this, hopefully, on the next slide. The amount of time between your 90 and 180 is the same as the time between the 180 and the echo, and you can do that over and over and over and over. So we should see, oh, my move is not in there. That's sad. It may appear randomly later. So you have this dependence then on the echo time for how many spins will come back. If you wait too long, they will start to wander off and they will not meet the criteria to come back as quickly as they left or return as slowly as they did. You also have to be slightly careful as your field gets rubbish, because whilst your pulse is on, and this comes back a little bit to long pulses, the longer your pulses are, the more chance stuff has gone wrong whilst your pulse is on. And so you will also see that you end up with some slightly off timings, particularly if you have a very short echo time. It might be, I took it off, that your echo has shifted by a pulse length away, which is why the oscilloscope is nice. Okay. We have a lot of things going on. Is everyone happy with this so far? Any questions? Yeah. So we have a lot of things which are bandwidth selective in NMR. Our transmit bandwidth and our receive bandwidth can entirely screw up an experiment. Our transmit bandwidth is proportional to 1 over the length of the pulse. So this is the equation about what we spoke about earlier. You literally divide the length of your pulse, or 1 by the length of your pulse, and it will give you the bandwidth of that pulse. So for a 90-degree pulse, you've got a quarter of a 360 pulse. For something like 10 megahertz with a 1 microsecond pulse, you end up with this weird distribution of frequencies, and you can excite these really, really wide bands of frequencies. If you were to go then to a millisecond pulse, at best you might excite a proton in the middle of your sample that's bang on resonance. Receive bandwidth is a parameter which you normally set on your instruments. I think we normally set it as the dwell time. Do you set dwell time on the... No, so receive bandwidth, very good. This one is important in terms of collecting your signals. When we digitize a signal, so we've got this thing which is wiggling around, there are only so many points on that you can measure. Mm-hmm. So our black one is our actual NMR signal, and I'm only going to measure every 1 microsecond. I will then end up with this kind of steppy thing, and that's what determines my spectral width or bandwidth for the receive. If I reduce the dwell time, I increase the bandwidth. If I increase the dwell time, I reduce the bandwidth. Both are useful.
Relaxation period.
I think it should be called, on this, the spin core, it's called spectral width. Mm-hmm. On the, I've not used the pure devices or Grunin's console, to be fair. But we should have a look what's on there.
Before we are applying the new pulse, at that time, development. No.
No. So the dwell time is within the point at which you're acquiring the signal. Mm-hmm. It's the time between each of the points you actually measure. Mm. So when we do, let's try and think what that will be called. So do you have digital points or receiver points or points per echo or points per FID, something like this? Mm-hmm. That is the number of measurements that you make over your signal. Mm-hmm. The dwell time is the spacing between the points, and then the spectral width is 1 over that spacing. If you have a very high spectral width, let's get this the right way around, you have a very short dwell time, mm-hmm. and you can get lots of points over your signal. So if your signal's a bit rubbish, that's useful. if you have a really long signal, like a beautiful FID, and you then try and cram in loads of points into it, you'll need loads and loads of points to get all of the way through the curve. And you then can afford to space them out and have a narrower bandwidth. All of that makes sense in practice, because if you've got a long FID, you've got a good magnet. If you've got a good magnet, you don't need to measure that many frequencies, which is why you have long FIDs and can have these. That's maybe all there is to say about that. We will go through this quite quickly just to capture a couple of things that are important. This is horrible magnet geometry where the field is really disgusting. So all sorts of different places, you can pick any different field. If you measure how far you are off resonance, you will start to lose signal relatively quickly. And the thing that is important for us is how much of that width we are exciting. And our transmit bandwidth is determined by the length of the pulse. So this is once again an important message about pulse length. If you are going to build a system, it needs to match power-wise something that will give you a sensible pulse. So it's no good having a really long pulse if you've got a huge number of different frequencies in your system, because you just will not be able to excite them. Okay, the problem that we also have in inhomogeneous systems is a 90 for one frequency is not a 90 for the next frequency. So I might do a 90 on resonance. I might do an 85, a little bit off resonance. Might only manage a 45 this far off resonance, and this probably doesn't even tip. If you do not excite a sufficient width of those, then you will pick stuff that's really on resonance, which can be useful. If you've not got much that's on resonance, now you've got no signal. Okay, so there's a lot of playing with pulse durations. When you set the pulse duration on a cheap magnet, there often isn't an answer. So you'll often see when you do a pulse duration sweep that you end up with these really wide peaks, because each pulse length is exciting a different volume of spins in your system. Okay. If your coil is not good, you maybe just excite everything not very well. If you manage to get a perfect 90, you will also have everything less than 90 pulse angles. If you have picked your duration badly, you can also have things that have been tipped past 90, and they will start to cancel out with stuff that has been tipped less far. So by having huge, great transmit bandwidths, you can actually completely get rid of your signal by cancelling it out with stuff that's gone past 90. So it's a really difficult thing to set well if your magnet is disgusting. The magnets we will build later are a bit disgusting. And so setting the 90 is quite a tricky thing to do to actually get things which are useful. Okay, we rushed through that a bit because the ins and outs of it aren't so important. Is everyone happy with the feeling that's going on with setting 90s? Okie dokie. If you have really wide receiver bandwidths, you are susceptible to picking up everything else that's in your environment. So if you are somewhere which is electrically very noisy, a narrow receiver bandwidth can be very helpful, but it means that you need quite wide signals. The best way to get rid of the noise from the environment is to use something called phase cycling. And phase cycling is the way that you can cancel out signals that are always the same. So there might be signals that you've created from your pulses. They might be signals that are in the background. But the idea is each time we do our experiment, we send our spins in a different direction. So maybe the first time we tip them this way, and we will get an echo that's this way. If the next time we tip them this way, the echo will be here, but the noise will still be this way. So you can cancel out by phase cycling each of your different things in the background. Your 180 noise from the pulse will always be in phase, and this is cancelled out beautifully just by flipping backwards and forwards and backwards and forwards. So this is the phase cycle for our to get rid of this noise. There we go. So we start off, we tip our spins this way, they dephase like this. We do a 180-degree pulse and they will come back and give us an echo. The next time we tip the other way, they will dephase and they will refocus and give us an echo that way. If you cannot change your receiver phase, you will get an up echo and a down echo and an up echo and a down echo. But all of the systems should be capable of going the right way up. This is okay, and it will get rid of 180 noise and it will get rid of systematic noise in the background at the same frequency, but it doesn't do a good job of getting rid of noise from your 90, and it doesn't do a good job of getting rid of noise which is slightly off the frequency that you're at. So we can do something slightly more complicated, which is to also change the way that you apply the 180. So we start off, you do a 90 one way, you get your echo one way, you do a 90 the other way, you get your echo the other way. Then you do a 90 the first way, but we do the 180 backwards, and then you do the same. So you're changing the phases of both of your sets of systems. This one is sometimes down in software as Cyclops. It's an acronym for something that I can't remember, but this is what it's doing. So you're doing all of the different phases to get rid of noise from other sources. Okay, is everyone happy with this so far? The problem with echoes is that this only works if nothing has moved. So if this one is processing at this speed and this one is processing at this speed, they will refocus beautifully to an echo as long as that one is still there and this one is still here. This is not what happens in samples which are natural. Stuff moves around because of diffusion. The consequence is your first echo is hideously diffusion weighted. Your first echo is dependent on diffusion times diffusion times diffusion times the strength of the gradient or the inhomogeneity of your field. That's really useful for us because it means we can measure diffusion, but it's also quite irritating if you've got a sample which diffuses a lot. So solvents are a nightmare to measure in inhomogeneous fields because they're moving around so quickly that you end up losing quite a lot of your signal that you start with. Fortunately for us, when we do this more and more and more and more times, everything after the first echo is only dependent on diffusion once, so not the cube of diffusion. And as long as our echo time is small compared to T2 star or compared to T2, you can do this over and over and over and over quite a lot. These sequences are called multi-echo sequences as a family. The ones which we use are either CP or CPMG, depending on the phase cycle. So if you were doing the first phase cycle, it's CP, which is car per cell, after the people that made it. If you do the right, left, backwards, forwards, up, down, cyclopsy thing, that's CPMG, car per cell, my boom, Gill, because my boom and Gill came along and went, why don't you change Y? That gives us a thing which looks like this. That's CP, that's CPMG. You apply a 90, you wait for tau, you will apply a 180 and you get an echo tau later, and then you can keep doing this over and over and over. In here, you will see these little curves, which is the dead time that we need to wait before we can start our acquisition. So once you have applied your RF pulse and turned off the amplifier, everything is going to carry on for a little while with some energy, and there's an exponential decay which will determine the minimum echo time you can set. If you try and squeeze these together so that you're requiring in this, all you will see is the grey bit. Okay. Nothing else on that. This is the scientific graph which shows you the difference between the first echoes and all of the other echoes. The first echo in a bad magnet might be tiny, and then it starts to get good from 2 onwards. Now here is the video. This is a load of our old students running around on a field. We wanted to repeat the analogy that I spoke to you about earlier, where fast things refocus fast and slow things refocus slowly, but they all come together at the same time. So we will have people run around and we count the number of people in the red box. We apply our first refocusing pulse and they will go backwards at the same speed that they started at. Then they carry on going in that same direction. We will apply a second refocusing pulse, and tau later they will come back into phase into the red box, and they keep running around, and over we do this. The analogy works really, really beautifully. The first experiment is hideously, our first pulse is really badly diffusion weighted. The people on the bikes really struggled to turn around, and the people that were wandering around in the middle really struggled to turn around the first time because they're not going at the same speed. After that, they stop counting and they actually come into some sort of equilibrium, and we will then get a really nice exponential decay over the top of our echoes as each time we do it, people get slower and go in the wrong places, okay? So this is what's happening with our spins. The more badly they have moved from where they're meant to be, the less signal they will come back with for our echo. Okay. This is the equation for the amplitude of each echo in a CPMG. There is an awful lot going on in it, but none of it is difficult. It's just there's lots of things. But the reason I want to show you the lots of things is because the CPMG is phenomenally powerful at measuring all manner of things if you know how to abuse it. The first thing is it has a dependence on T2, which you would hope, because we're seeing this dephasing in the XY plane. But the things that we most care about is it's dependent on diffusion, it's dependent on the echo time, and it's dependent on how inhomogeneous your magnet is. If you have a really inhomogeneous magnet, you will see this drop off very quickly. If you have really strong diffusion, you will see this drop off really quickly. If you have a really long echo time, you will see this drop off really quickly. If you reduce any of those, it goes long. So if you have a really nice field with really short echo time and almost no diffusion, this will go on for ages, and it's just determined by T2. At the point at which any of the other things start to happen, then you start to lose them. M is the number of the echo, and TE then is your echo time, so it works out where it is on the exponential. The last equation, which was just for the first echo, is pretty much this, but with D cubed. So your first one will normally, in a bad field, will be small, and then the rest should follow this echo train. The thing which the community does not agree on, and it's because the community comes from high field nice magnets, is the names for this. And you will often see the decay over the echoes labeled T2. It is T2 if none of this is true. So if G is very small, sure, that's T2. But the point at which you move away from infinite homogeneity, it starts to not be T2 anymore, and we call it T2 effective or T2F. So the decay over the echoes is T2 effective. The slope of each echo is T2 star, and T2 is a thing determined by your sample that you can measure by tweaking this around and playing with it to get another graph like T1. Does that make sense? This is the kind of rubbish that you get first time build a magnet and try and measure it. This is a very poorly optimized open system. SNR, not very much. It's maybe 2 or 3, probably 2, maybe 1.5. Very, very noisy, very, very difficult to truly believe there is an exponential there, but those dots are slightly higher than these dots. If you work a little bit harder.
Not to explain the SNR, we want to show that what is.
Shall I explain SNR? What a wonderful idea. Signal to noise ratio can be measured in 2 ways. The way which I think it's best measured accounts for what's really going on in the system and gives you a better number, which makes your systems look good. The way we work out signal to noise ratio is you measure what this value is up in the corner, which is your kind of maximum signal that you can get. Then you divide it by the spread of the noise at the end. Okay, so to measure signal to noise ratio, you need to get to the point where you've come into the flat bit. You measure the spread of these points, best with a standard deviation, but you can guess just by looking at the top and the bottom. And then you divide the number up the top by that. So a very quick rough guess, the number up there is about 150. This spread is something like 50, which probably means its standard deviation is something like 25. So we divide 150 by 25 and we come out with quite a depressingly low signal to noise ratio. If we do the same experiment this side and we divide 150 by 149, we've got a very small signal to noise ratio. When you have a signal to noise ratio of 1, there is as much signal as there is noise, and you can at best guess that it is signal. At the point at which you have a signal to noise ratio of 2, you can claim that you can see NMR. You shouldn't to anyone other than your very closest friends. By the time you get to 3, 4, 5, it's as good as NMR. NMRs on kits like you have in the lab are probably in thousands. Erdem, what was yours when you got it? Nice, 1,000 and something. Yeah. So you can build these and get thousands. Everything that we've looked at so far is all you need to do to improve the signal to noise ratio. So if we put this in a box, we don't improve the signal, but we reduce the noise. So you get better SNR. If you improve the homogeneity of your magnet, you will polarize more spins and you will have a higher signal for the same noise. So you will have a higher signal to noise ratio. So each of these things can be changed to give you better signal to noise. Thank you. That was very useful.
Honestly, my problem is to decrease the sample size, tube size a lot. Some other signals could affect my signal.
Yes.
Or there are unreasonable peaks.
Yeah.
Like that,
Yeah.
Still gives the nice SNR, but it's meaningless. Best way is the shielding.
Yes. So the best way to improve SNR is to eliminate noise or to completely optimize signal. So if you make your magnet nice by shimming it, by tidying it up, by really simulating it well and perfectly positioning magnets and optimizing your materials, you will get the best SNR in combination with lots of shielding. We are not going to go through this. Suffice to say that in an inhomogeneous field, this is the magnet and the RF coil, things will not do what you expect them to do if you apply the same logic as you apply in a beautiful system. Okay, things are slightly different. The big difference is, unless your magnet is quite homogeneous, every single RF pulse that you apply will not excite your entire sample. Okay, you are always going to be in a smaller volume than the whole thing. So a little bit of care is needed. Okay, so that leaves a small number of pulse sequences that we can use on cheap magnets. CPMG, which we have seen, CPMG that we have seen, and pretty much CPMG. If you work really hard, you can get it to give you a Hahn echo from 390s, but CPMG just cancels so much stuff out that is by far the easiest thing, which means that we need to do some stuff which is slightly more clever to be able to measure anything. T1 is the most varied, and there are lots of different ways you can do it. If you have a really inhomogeneous magnet, so something like the unilateral systems, you necessarily have a huge gradient. So our benchtop mouse system has a gradient of 11 Teslas per meter, which means if you measured a distance of a meter, one end is not 11 Tesla, but one end would be 11 Tesla and the other would be 0. So it's this huge, great change, which means that the spins excited when you do 180 are different to the spins excited when you do a 90. because you have these different bandwidths and you have different powers and you have different amounts of spins that are underneath what you're looking for. So the traditional method of measuring T1 is quite difficult. There are 3 steps to any T1 experiment, regardless of how you do it. The first is you do something called preparation. So you take your magnetization from Z and stick it somewhere else. Traditionally, it's opposite Z, but you will have spins that are opposite Z and a bit less opposite and a bit more. So that doesn't work very well. You then wait a bit and you let it wander back towards equilibrium, and then you tip what's left back into XY, and that's what you measure. You then change the evolution period and you measure it again, and you'll get more and more and more into the XY plane until you've got your curve. So the different ways you can do that is the traditional method, which is inversion recovery. So you take all of your magnetization, you do a 180 and it will stick completely down. You wait a bit and then you measure once you've done your 90. And stuff that has moved very slowly after you've done your 90 will still be measurable. Stuff that has moved very quickly will be measurable with a different phase. And the stuff that has perfectly reached XY will now give you no signal because it's pointing back along Z. You then wait a different amount of time. So now we've gone much more quickly, and now everything is giving us some signal. So we can see the different times, and you will build out a curve that gives you T1. We can't do inversion recovery on a magnet that's not good. You absolutely cannot do inversion recovery on a unilateral system unless you work really, really hard at getting a perfect 180-degree pulse, which is difficult. This is inversion recovery, 180, and you change this time and you will chart out the T1 curve. A different way to do it is something called saturation recovery. Saturation recovery does not rely on having 180-degree pulses, which might be a bit rubbish. Instead, you poke it over and over and over again with 90-degree pulses until you have shoved it all of the way back around to 90. At that point, you have picked where your spins are, and it doesn't matter how imperfect your pulses are, because if the spin is in the wrong place, it was in the wrong place for 5 90-degree pulses and it no longer cares. So you only refocus the ones that matter when you do your CPMG sequence. We tend then to keep the CPMG sequence quite short in terms of its echo time and just add together a load of echoes. So we start off and we have our saturation. This is sometimes called saturation comb recovery because it looks like a comb. And you start off with a 90 and you wait a bit and you do another 90 and now they're pointing down, and you wait a bit less and you do the next one and the next one and the next one. Then you wait and then you do your CPMG. So this is like inversion recovery, only instead of starting from upside down, you start from XY, which means you don't have to wait quite so long to do your next experiment either. So this one's quite nice because you can do this much more quickly than you can do an inversion recovery anyway. The other way to do it is best described as the way to estimate T1, but it gives you an okay answer. And as long as you always use it, you can watch T1 change. And the thing that's nice with this is that you don't need to change anything. So you can build a spectrometer that can only do a CPMG, and just by changing the parameters, you can get an estimate of T1. If you remember back to our requirements for doing our experiment again, we needed to wait 5 lots of T1 for our magnetization to come back along Z. If we didn't, we got less signal. So we don't, and we get less signal, and the amount less signal you get is proportional to T1. So you just do shorter and shorter or longer and longer repetition times from something short, and you will chart out a graph which should relax with something a bit like T1. And that is by far the easiest way to measure it. You can just do it out of the box. You don't even need a sequence to do it. You can literally do it and write down the number. Diffusion then is another thing which is quite nice to measure in an inhomogeneous field. Diffusion is hard to measure in a nice magnet because you have to add a gradient, like you have in the pure devices one. We don't need to do that because it's in there already. It would be nice if it was all in one direction, but it's okay. As long as you know what it is, you can measure diffusion. And the idea is that we can change how much diffusion weighting you are getting, so how badly affected by diffusion it is, by changing how long the echo time is. If you have a short echo time, I can only get from here to here, so I can only be so badly off being refocused. If you wait ages, I can, not going to go down there because I fall over, be the other side of the room before you've tried to refocus me, and I will not give you any signal. So the longer you wait, the worse, or the fewer spins will come back and be refocused. Exactly like measuring T1, you wait a bit longer and a bit longer and a bit longer, and you will get less and less signal each time. The trick, which is nice with CPMG, is you can then go from this echo time, which is giving you diffusion encoding, and then go hell for leather as closely as you can space your echoes with a really short echo time. And all of these should have about that same amount of diffusion weighting. You can then add them all together, and every echo you add gives you another contribution to your SNR. So by doing loads of echoes here, we can improve our SNR without having to change anything. And we just change that first delay. You could do the experiment without doing that. You can just measure the first echo, or you can suffer a bit after, but it's a nice way to get a bit more signal to noise ratio for free. The equation for measuring diffusion looks hideous, it looks ugly, but is just the same as before. It only has stuff in that we know. Okay. If we are just looking at our first one, our first echo, we can use this. This is our one for our CPMG. You do need to know what your gradient is. And the trick is you take a sample that you know T2 for, and you stick in all of the numbers, T1, T2, and you can work out what G is. And then you move to things that you don't know, and you can work it out then for T2. T mix is the amount of time that you're leaving at your evolution time. And it just gives you a really easy way to very, very quickly measure diffusion without having to have any other kit. It's the only thing that we have going for us when you have unilateral magnets and when you have really poor homogeneity, is you can measure amazingly fast diffusion, which needs a huge gradient normally. So the unilateral systems have access, a bit like the fast field cycling stuff, where you can get to regimes that you can't normally get to. If you have a magnet that most of the time gives you a real headache trying to get anything out of, it will measure diffusion beautifully, which is quite a nice experiment. Okay, so I just want to quickly go through the process that we follow to pick what the parameters are and the steps that we go through to do that. The most important thing when testing anything that you have built is to use a sample that you truly understand. You should also use a sample which is unchangeable. So our preferred thing is like vegetable oil or corn oil or some kind of cooking oil. We like it for several reasons. T2 is long, so you have plenty of chance to collect an echo. T1 is really short in comparison to water, so you don't have to wait long to do your next thing. And if you're going to do 5,000 averages, it's nice to not wait too long. Number 3, I can leave a bottle of oil open on the desk for a month and come back, and it is the same as it was when I opened it. If I open my bottle of glycerol and walk away for an hour and come back, it is not how it was when I opened it. And the amount of water that is in glycerol will change T1. So we do not like glycerol for setup. What we do like glycerol for is adding water to it changes T1. And so you can do water glycerol mixtures and you can check that there's a sanity check that you're getting stuff that is sensible. So we will always start with oil. In order of appearance, the parameters then that you have first off are your pulse lengths, which we've talked about a little bit. And the way that we set that is to sweep the pulse length. When you reach a 90-degree pulse, and bearing in mind we're doing this with a CPMG, so all of the time you are effectively changing 90 and 180. 180 is always double the 90, either in amplitude or length. And you just do your experiment with a pulse length and you measure the signal. You change the pulse length and you measure the signal again and you look at how big it is. And you keep doing this and you will trace out a very pretty graph that at some point will reach a maximum of some sort. This is probably your 90. The only way to be sure it is your 90 is to keep going until your signal disappears. At the point at which you have a 180 and it is double your 90, you have found your 90. We build many magnets where it never disappears because there are places in the magnet where your 180 is actually doing a 90. Pick one, do an experiment. As long as you are getting signal, the signal is okay. The bigger the signal is better than setting it to half the point at which you've got rid of the signal. If you have a magnet like that, there is no hope ever of measuring T1 with inversion recovery. If you do get a nice up and a nice down, inversion recovery works for measuring T1 because the 180 actually does a 180. So that's a 90, 180 is double of a 90. Tau then is the next thing that exists. The echo time will always be twice tau, so the same discussion applies for both things. If you set tau to be very short, your lower limit is the ring down, so your dead time of your system determines your shortest echo time. In your echo time, you need to fit your dead time and the width of your acquisition and your dead time again the other side because the echo is in the middle. That kind of gives you something which is probably on the order of 50, 60, 70 microseconds. And if you go shorter than that, you just see all of the pulses everywhere and you will never see a signal. Yes, please.
It's better to choose the short tau to see the signal coming from the solid part.
Exactly. So the shorter tau is, the more stuff or the more likely you are to see things that are solid. Systems that are built to measure solids, lots of effort goes into making the dead time short. So that's this is pretty much the limiting factor for your echo time. I could, if I wanted to, just measure one point at the top of the echo, and as long as that one point is in exactly the right place, that's fine. However, this will bump into this quite quickly. So the Fukushima book that I showed you yesterday has a whole chapter devoted to reducing dead time for solid systems. But the short of it is you basically make your system rubbish. So if you are not well matched and you have terrible match over a really wide range of frequencies, it's very difficult to make it resonate. If it's not resonating, the dead time is short. In commercial high field systems for solids, you have magic angle spinning, but before that, they sometimes put something in called a quench. And the idea is that as soon as this happens, you basically desperately try and kill that signal. And that allows you to reduce the dead time. If you've built a duplexer out of quarter waves, if you have 5 quarter waves, you will have a shorter dead time. We did an experiment some years ago on the MRI where we built a new duplexer and we did 7 quarter waves, and 7 quarter waves has a dead time that is almost irrelevant and you can really push it down. If you want lots of diffusion weighting, you do the opposite and you want to set a really long echo time. The let's see whether we can draw a very quick graph. So if you think about a given sample for a given T2 and a given T1, I will change the color if that can't see it. So if you've got a sample and it has a very long T2 and a very long T1, in order to measure this sample, I can get away with a long echo time, or I can get away with a short echo time. It doesn't matter, because my echo time is going to select things that are this side. T1 needs to have a long repetition time, or I'm going to lose the signal from this. So our repetition time is going to set which things this way we can't see. So if I set my repetition time below this level, I will lose the signal from this. If I'm in this corner and I have a long T1 still, but a short T2, I still need a long repetition time in order to get the T1, so as not to lose the T1. And if my echo time now is too long, I will not see this because it will have relaxed too quickly. So the way that I like to think of it is that your echo time gives you stuff that's this side, and your repetition time gives you stuff that's this side of the line, and you can move them around to cover the bit of the graph that you need to cover. If you have a long T1 and a short, a long TR repetition time and a short echo time, you will collect everything. So in MRI, we call that experiment proton density. It's basically measuring how much stuff you have. Then if you want to see the effect of T2, you increase the echo time. If you want to see the effect of T1, you reduce the repetition time. Dwell time, or spectral width, or whatever it is we're calling it, will determine the basically the range of frequencies that you are sensitive to in your system. The wider the spectral width, the shorter the dwell time, the more likely you are to capture signals if you've got a really inhomogeneous magnet. We will always start short. So out of the box, we will start with a dwell time that is half a microsecond, or a spectral width that's a megahertz, hertz, whatever, 1,000 kilohertz. So that we make sure we're capturing everything. At the point at which that's giving you an echo that looks like this, then we will reduce the spectral width down until you get an echo that's a nice shape. So we will always start short with dwell time or long with spectral width, and then work that inwards. Are there any other parameters that we've not done? Pulse amplitude is one that might be fixed, but it works just like the pulse duration. So you can do the same thing and sweep the amplitude until you reach the equivalent of a 90-degree pulse for that amplitude. The frequency tuning is possibly the hardest thing when you have a new magnet that's inhomogeneous, because when it's new, you don't know the frequency, you don't know the 90, you might not know the pulse amplitude, might not know anything about it, and then you just have to persist. We measure the field with a Gauss meter, work out what the frequency is, set the frequency, sweep the 90. If it's still got no NMR, we change the frequency, and you repeat the whole process over and over again. But we persisted until quite late yesterday, and it worked. But that is the process by which it goes. And it's hard if you've got something and you know nothing about it. You can do things to make it easier. You can use coils that you know the properties of, and you can make life easier for yourself. But at some point, you will get to an experiment where you just have to do everything. We wrote a bit of code when we were away last time that sweeps all of those things and gives you this huge 3D plot. And that's nice because you can leave it, but it still takes 5 or 6 hours to give you an answer of each of your 90-degree pulses for each of your frequencies. I think that's all of the parameters that are in a CPMG. Does anyone have any questions? Then it's lunch. So we're not coming back here. So we're back in the lab this afternoon at 2. Perfect. Yes, yeah. Oh, yes. So those online, thank you very much for coming. Unfortunately, you don't get to build probes with us this afternoon, but hopefully it's been useful.
Şey,
Nice, in the deep end.
Ben kamerayı mı kaydettim Eren? Yoksa genel şeyin hocamı mı? Bir dakika. Ses kısmı. Sen de bu kamerayı kaydet ya.
There are slightly more than perhaps hits of. But we start off as one of these pairs, and then you can each have a go at each of these. It's separate. The bottleneck for today is we only have one console that we can test them on. So our plan at the moment is we get you all to build these, and I'll talk through how you build them. If you were happy to build them. But then we'll probably get you to come up a few at a time and come and test them, and then we can carry on with the next bit and then give it time to make it easy to get on the Once we have built these ones, which I think are the easy ones, we will build the extremely hard ones, which are the Lego kits. At the moment, Lego kits are fresh off the loads of and each of them are individual bricks. When we make these, they need to not be individual bricks. I'm going to get to glue the bricks together. We're all helping to make it. Once we've got those built, then you'll be able to put magnets in the lower coil. These ones, even if there were enough for one each, I won't put them two. They're quite tricky to build and to hold together once you try and start them. The magnets which we're using today are real magnets. Real magnets bite, and they bite, and they're quite painful when they do so. So we have the risk assessment of how to use them. I will quickly go through safe handling with magnets, and then before you touch magnets, we'll just get you all to have a quick look through and see that I've told you what it says, and you can sign it, and then everyone is safe. Would you just go to that drawer? So these are the magnets which we're going to be using in the Lego probes. On their own, they are not too bad. On their own, they're not too. It's a plastic fine, it's fine. On their own, they're not too bad. If you take them near anything which is metal or worse, another magnet, they will very quickly, desperately try and attach themselves to said thing. And if it's your finger in the way, it's not particularly nice. So, when we handle magnets, we wear gloves. We have many gloves. If you are handling magnets, please wear gloves. These magnets are not too strong, and if you get them either side of your hand, they're not dangerous, and they're uncomfortable. But if you've got the gloves on, it gives the magnet something else to pinch. So it will pinch this instead of your skin. It's when you get just a little bit in between. It's when you get just a little bit in between that is the problem. But on their own, they're actually not too bad. Even if you do manage somehow to get them, they're absolutely fine. Nothing bad. It's the little pinch that's quite painful. If you've got the gloves on, it will do that to the glove instead of your skin. It's painful on your skin. Magnets do not pull apart this way. You will never, ever, ever get them apart if you try and pull them this way, because they're too strong. They will slide. So the force that way is not very strong. Shear is not good for magnets. In that way, it's really, really. When you've got the magnets, we slide with it. Throw with gloves. So that's pinching. We also have some tools kicking around, which A are magnetic and B are pinchy. So please do not put your hands in pliers and squeeze. Same goes for physical squeezing, which will give you a slightly different type of injury, but nonetheless pleasant. When you are doing the gluing, we are going to glue with super glue. This is very liquid super glue, because it dries very quickly. It also runs off of all things. Yes, phones and magnets are that. So the first thing is, if you take phones close to magnets, it keeps you close to the pace of the phone and it shuts it like it's got the magnetic pace. It shouldn't mind too much, but I wouldn't risk it. They hate credit cards. So do not put bank cards near the magnets, or they will no longer be bank cards. They're fine chip and pin, but they will not work for the people who work magnets. It's not good. So this is very, very liquid, and it pours very, very easily. Definitely not open desk in my hotel So just be careful if you've got the lid of the bottle. Do not touch the glue to your hands. We're going to try and find some gloves, different type of gloves to these type of gloves, normal lab gloves. So make sure you've got something on to protect your hands. Please do not tarnish the beautiful lab spaces with super glue. When we're doing the gluing, we're going to do it outdoors, and we've got some paper on the table. We'll also get you some paper wipes up there just for it. Do not smell the glue. It is very unpleasant and bad for you. It will stick your nostrils and eyelids together. It's nice. Thank you very much. So just be careful with that. Other than that, it's perfectly safe. We are relatively well ratioed, so there are 4 of us here who very much know what we're doing. Within the 4, it's varied. There are some of us here that know more than others. There are 4 of us here that do really know what we're doing with these. Please ask if you are stuck, and we will show you how to do it. Something else I was going to say called sound. Sorry, Mrs. Would you like to bring it?
Maybe it's better if people price it.
I start the instruction manual. And that's for this as well. Depends on how far we get. So if you just name the side of that, depending on how far we get with the first, it may be the manual. So, I think at the moment we are not office and we are very stood up. We're not just sat down, it's much easier to do it. So, yeah, I don't know. So I don't know whether just to quick pairs with kids and then you can find a space to work somewhere on the seat. I will show you how these go together. I've been you said that now I think this is but it looked very nice. So in your kit, you will get a straw with 2 bits of wood on, which will show you where the middle of the magnet is. So the magnet center will be between 2 wooden bits of the straw. To connect to the console using the matching board, you need 2 ends of wire. Okay? There's 2 crocodile clips and they each go on one end of the wire. You need to make sure that whatever happens on this, this happens at the other end. So don't start at one end down here, which will end up with one piece of wire and you're not going to. So leave a little bit dangling. And then you want to try and get 35 turns of wire on. Yesterday, how to make perfectly efficient RF coils. You're not going to get that in this space of 35 turns of wire. The neater it is, the better it will be. But you're not going to get the perfect RF coil because there just isn't space. And the wire that you need to do that is just right to put it. So try your best to wind a really nice coil in there with 35 turns. It doesn't look like this. And you should end up with something like that. Okay? So that would be your RF coil. Tuning and matching boards we put next door. Fine. Thank you. This wire works for winding RF coils because it looks like wire, but it is not really wire. It has a plastic coating on the outside. So these are not touching each other. They're connected to each other. That does mean that we can't connect anything to this. I have one. So it does mean that there is no. So we have a couple of files sticking around on the data and just file off the plastic. Plastic has been filed off the colour, so you can see. We can try lighting it. Sometimes the problems they stick and then you solve it together. But by all means, try it. Once we've got the RF coil, then they clip into these boards and that will connect it to the spectrometers. These then have magnets in. So again, you don't need the gloves on for these because they're relatively well protected. If you try and hurt yourself, you will hurt it. So just be careful with handling. They're relatively safe. These go together with the top one, which has a notch and a wire to go through, the bottom one, which does not. So if you look at the logos, you can see the bottom one and the bottom, top one. With the RF coil, and that will hold it in the right place at the sound. So that's now in the middle of that. You can then stick its other side on. You just need to make sure the front half is on the same side, because that's where the left is going to go. If you stick one on upside down, the power. That then should slot easily to the other side. So, and then you choose your preferred, I missed the one. Choose your preferred logo to have outside. That's one thing you miss because the can logo comes through. So why should come through the notch on the top. And one side, and the side, so they should. Final job is to slip on the camera, which they might use to try and get it in. The heat of the coil will get to the NMR will be. I think you spend the next 3 hours winding a coil with a straw. Disappointed minutes. When you think you are ready, let one of us know. We could try it on the console. We've got 2 network analyzers next door, and these boards don't need tuning and matching. They are. So we tune and match these by changing the number of terms. As long as it's close, it should be fine. But I just want to see if it's a problem. Comes on, it comes on. Is there a else? Yeah, so we'll measure the field with the gas. I think that is a sufficiency of information for the moment. Yes. So these fit standard NMR tubes. There's a variety of things in there. So this is our favourite corn oil, and that should, in theory, poke down the straw. And that should be thing. We've got different things to test. If it works very easily with corn oil, some different things. It might be that we're something called dry trying to get some Okie dokie. So if you assemble into pairs of some description, thank you very much. Magnets.
Yeah.
We passed it round. So yeah, who was not sideways? Who was not? But yes, that would be a really clever way to have organised it. Very nice. First up.
Did you open? They're perfect. You picked the only one that. You need to read the other things, but it's fine. He went through this. Because we're going to handle the magnet, so yes, it's a new one. You know? Dilara ne hırsız, Dilara ne hırsız. Dilara üstünden sarmıyoruz değil mi? Sadece mi saracağız?
Neyse, şöyle. Mesela hocan soruları yapsın.
Yok yani.
Tamam, hep homojen.
Bir de şöyle yaptı. Ben öyle izledim yani. Erdem düzeltsin yapmışsa. Böyle şu şekilde tutacağız. İkisi de eşit olacak. Ortadan sarmaya başlayacağız. Şöyle değil miydi? İkisi birlikte sarmadı.
Dilara. Dilara. Dilara kazanmışsın. Yani sadece tabak tutmak. İnce bir iş yiyoruz. Ne kadar kötü yapıyorlar bir bak. Nasıl kötü çirkin olmuş öyle izliyorsunuz. That looks really good. Yeah.
There should be a file here with a gray handle.
Struggling. Another group struggling. Erdem sanatçı.
Bence okey abi ya. Ya denersiniz. Robun sardı da öyle bir şeylerdi. İstersen geçsin abi.
Struggle.
Şöyle bir parçayı şu kadar, çok göz kararı da olabilir. Yani şu kadar yeterli ama her taraf.
Kaydoluyor. Sen bilirsin.
Daha sarılık sırada mısın?
Şey dedi. Excellent.
Ama yeni bir daha sarılık. Benim bir zaten şey yaptım. Şu standart orada mı var acaba?
Hocam bizim bitti.
Şey Erdem, standart koyacak mısın? Şunlardan orada var. Hazır. Ya zaten sadece şeye bakacağız. Çok kesinlikle bir şey fırsat çıkarmamız lazım.
Tamam, şu kadar şunu bırakmışsın. O kesmez, daha keser bir şey.
Kesmeyi kesiyorsun.
Üçüncü fiyatımız fazla geldi. Aa, 5 ton yaptım. Yapmıştım.
Bu kadar uzun kalması için normal.
Pakette
Kaç
verdim.
sene dağıtıp üstüne sonra fiyat getirdim.
Ne yapıyoruz törpüyle?
Lastik kablosunu çıkartıyoruz ki. Şu an yapmana gerek yok.
Sena yapamadım, bırak Sena. Sena kaybedeceksin. Kaybedeceksin, bırak. Yok. Hayır. Bir başkası var.
Okay, so let's take a
Şu an amacımız şurası içinde oluşan alan 5 ise buradaki de 5 bunlar sabit düşüyor. Bunlar da beraber bunlar oyun yaratıyor. Gerek yok. Canım o 5 ulaşmak geç kalmıyor.
Nerede şahin olmayan görüntü böyle bir şey mi?
Şahin olmayan.
Bant.
Abi bu ismi kadar şey. Bayağı şey. Erkekler yalnız kızıyor.
Sizde ne kadar rekabetçi çıktığınız zaman
Zaten değişiyor.
tamam.
Yani çok küçük olmasına gerek yok. Yapabilirsin.
Şu an dışarıda kaldı.
Kanka bir tane daha var. Bunu da
Şunu buradan getir.
oradan.
Ama buradan getir.
Don't worry, I think they done this for that purpose. Have you ever varieties on your oh, you need to know the number. Oh, okay, because that's important for the frequency. And otherwise, two prints. Otherwise, we can still arrange the variety. Yes, I don't think it will shift it too much. Yes. Try to be even. No, no, no, no. Yeah. It's really hard to make it perfect. Someone get a signal. Yes. Які облоги SuChAQuality? Ne kadar doğru? Üstündeki coating'i aldırayım.
Now we are about to this is
They will have a sample.
Başka var mı sizin şey? Var. Var. Seçim.
What is this? Sugar. Sugar. It's an old sugar. Sugar.
40% maybe. 5 tane.
Şu an olduğuna yaklaşmış olabilir. Çünkü onlar daha fazla.
Sorry, sorry.
We've never built one that's like that well before. Wow. Wow. It's 1, it's like 0.1. So you've got over 10. Wow. Wow. Oh. Yeah, so that the exponential of that is t to the effective. Every average we do, the SNR goes up and up and up and up. That's really good. So it is a shame, but we are going to do a screen shot. You can remember where print screen is. This is the picture that we should use in the future.
Yeah. This is what your probe should look like.
Very nice. Well done. So slow. It does preserve the battery at least.
1.45.
145.
145.
142 grams.
Into the box. Good touching. Yeah,
Aha! There we go.
now we're waiting.
Nice, very nice.
Down.
So the software for this console is licensed. I don't have a license on my laptop. So this is some Python software that I wrote so that we can still run the console if we didn't have a license. Nice, there we go.
Pardon. Sen mi?
Very nice. Science. Yes. Yeah, quite a long way.
Can we do the sample now? Or no?
Yes, do you want to stick in the,
We need it for another?
So we're just going to quickly stick in the sugar syrup. Whilst I put it in. So at the moment, this flattens out around 100. And 32 repetitions, and that's what I reckon. So that's about 0.75. Oh, right.
What's happened?
No,
You save it?
I'm not gonna lie there.
Okay, but now the sugar syrup is so now the decay is much quicker. So the sugar crystals in the water make T2 shorter, makes T2 effective shorter. So you can use that to look at the concentration of the sugar, so the more sugar there is in the sugar crystal. Or you can look at it to have the size of the crystal is different. Yes, at the moment, all we care about is sugar. We look at steps. So this is how strong the magnet tests. And so when we get into the ready, it's so nice. Come through. Come through.
Sounds like a doctor's voice.
Yeah, doctor will see you now. Okay, dokie, and then we'll start off with corn. I've already forgotten what it's not like
This is what I did the other day.
yeah, it just sometimes happens.
Expecting the Python code to actually
to open again.
It just gets tired after a few frames.
It doesn't like it when the keyboard falls off. It's the same as keeps making my laptop go black in the lectures.
Is it when it disconnects?
native fruits goes away.
Get too close to the house. Yeah. We just say don't put your frozen on.
I'm getting a headache. I'll come back. What is it?
So this is the shielding.
Okay.
So hopefully this will cut the noise down enough that we can see the signal. If we left it out, probably have this in our
I think we're going to need to restart the computer.
No! Don't say that. Crash. We have to restart the computer. Should we start
So
doing
we'll
Lego?
start Lego.
And we'll come back to this.
Nazar değil.
Should we take them
Evet, enerji.
Okay. Thank you. I don't know whether we'll have combined gluing and spray.
This is the next one we're going to do.
Oh, yeah. You mentioned that next one.
Yeah. It won't have this.
It looks easier, but I'm not sure.
Yes, do not be deceived.
What really is this difference?
So this has eight
Yeah.
magnets in it.
Ah.
Yeah. So there's a Halbach array. I won't take the top off. There's probably your 2 pole magnets, and then around the side you've got the ones that change the field. And then your magnet field will go that way through the probe. The coil goes along that way, and then that's your setup.
Oh, hang on.
You're in. Back.
And something magnificent.
Cotton foil was fantastic.
That is
The
amazing.
coil was fantastic.
Yes, I
Yeah, there you go.
really worked
Yeah, it
on.
was worth it. Thank you.
Fantastic.
This is really amazing. No, no, this is amazing. This one. Who's this coil? Wow.
Yeah.
It's great, isn't it?
Yeah, that's amazing.
Oh.
So you have signal.
Beautiful. Okay, look at that. Lovely, lovely, lovely.
So the trick is get other people to build them.
Well, the trick is building the coils patiently rather than doing this,
Not doing this.
like we normally do.
We build it really regularly.
It makes a
so
massive
that is
difference.
perfect.
Makes a massive difference.
It's very precise.
It's increasing. Yeah. Okay.
Like man, always do it.
Person
Yeah.
doing this kind of detailed work.
That's it.
Yeah,
Lovely.
Yeah, it's getting better.
Right, what was the sample that you've got there? Nice. So let's swap that one out and stick that one in. So this is dropping down here-ish. So you're sort of at 0 at this point here somewhere. It's a little bit bumpy there, but if you look on the line there, you can see it. So if we pop that into there, yeah, make sure it goes all the way to the bottom. Otherwise, it sits just above, and that's quite annoying. Okay, so that'll drop down about here, but this one now has got absolutely no signal down there whatsoever. All of the signals here, so we're going to have a much shorter decay, and because of the crystals in the sugar are reducing T2 effective, reducing T2, and that's pushed all of the curve to the left.
And it's bottom of this rope. There was some.
Yeah, there's crystals in the bottom. If we pull the tube up so it's the crystals in there, we'll probably get almost no signal, because they're so short, we'll have pretty much nothing. But in here, where it's still syrupy with some crystals, you've got enough. Very nice. So, how many more codes have we got to go? 1, 2, 3, 4. So what we might do is I might set everyone off doing Lego, and then we'll test your probes. I can go. Oh, in fact, this is exactly what we're going to do. Now it's your problem. Do not forget to push stop. Always stop. But what will work? So you can wobble, make sure it's sort of
Yeah.
You don't need to choose that.
Should have had it. Yeah, completely.
And this is like shows us.
You could then do a better experiment. But one of the things that's right now is we can make time focus. And once the thing is like, that's so better. That's so better. Okay, so now we need gloves. Yeah. Oh, yeah, just get one. Yeah. Yeah. So this is what I'm going to do now without a bit of bottle because I have my paper person. The first thing is to glue together these stacks of bricks. Okay, so in the bag are bricks. And you just need to make sure that one big. That was your one bag. So, what we're going to do first is take each of the stacks of bricks in here. There's two types of holes. One type of hole is at an angle. We don't need these yet. One type of brick is not at an angle. There are two different colours with the one I'm telling you. There are two different colours with these ones that are square. Like powerful ones. Yeah, so there's three types. There's circles, big circles, diagonal ones, big diagonal ones, and just these ones that are flat you want to do. And you want to glue them together as stacks of 5. 4, 5. So you should end up with 4 grey stacks and 4 not grey. Sandy colour. So you should end up with 4 of each of those. Put them together first, because if they sit funny, they're being cut and they won't go together. We just need to find them first to make sure they fit together. If they do fit them together, start to glue them. When you glue them, make sure the spots are aligned. Get them crosswise, you're not going to fit them out. So make sure they're both in the same direction so you can see through the square. Once you've managed to get them glued, just leave them to dry for a bit and we'll have a break. Once they're all dry, I found it easiest to glue them. I put the magnet down, put in glue on it, and then stick the next one on top of it, rather than picking them up, because otherwise you'll glue yourself to the magnet. They have little bamboo sticks, and they work quite nice to take the steps out. I think they come out a bit aggressive. They're not. We'll just take the steps out. Okay. So, and then if you just give it a little dip, you can paste it just into the gaps and then drop the next brick on top. I guess not to touch it or glue it to yourself or anyone else on the table. And then once you've got your stacks of 5, does anyone have any questions about gluing together? So we don't need to glue both ones at the moment, just just the one foot at the front, so not the ones at the back.
5? Okay.
5. So you should, yes. No, that's right. So you should have 4 of those and 4 of those. Stacks of 5. You have 4 stacks of 5 bricks in sand and the same in grey. So you should have those ones. 4 of these, 4 of those and 4 of those. You don't need those ones. Just one for the square. yes, I'll keep the kids together. Stacks 5 high, 4 lots, 5 high. We should have bought magnets only in 4 bricks. So if you take your kids outside and then we'll glue them in the garden. And this is
Yes, good idea, yeah. We're gonna bring these outside, the sticks ready. Make sure you have gloves on. They should be outside.
Sonra bunu devam edelim. Bu bizim bıraktığım yazı. Ve bunları herhalde demek istedi. Oradalar değil mi? Hala geri ben yaptım.
Olmadı.
Tekrar yapıyorsunuz. Bir de olmadı. 5'ten fazla geldi. Ben strese bak, stres geldi bana. Bir de böyle eleşi, bir de başarısız olur ya ben böyle şimdi. Bence de öğrendik. Hadi bir daha deneyelim. I'm trying again. I want to get a signal.
Oh no!
Because my turn is too much.
I have to take some off.
Yes, I think and I will try again, but I don't know if it's word or not. Does that work? Yes. I try something to do, but I don't know if it's word or not.
Make sure to get through the gap.
I cannot do this.
You're missing.
This one.
Make sure the coil's in the middle.
Okay, thank you so much. Tamam. İnşallah çalışacak. Neden çok tatlı? Çünkü sen mi kötü? Bakın hiç biraz daha şey. Tekrar ölçüm aldım.
Ama şey gerçekten tamam. Yani
Şu bizim. Ne ki o? İşte yani falan. Daha ilk şunları yapacağız.
You're trying to.
Yes.
It's a long while.
Yes. But I had the right adapter earlier.
Which one?
Oh, it's on the gas. I put it on the gas.
Oh, okay.
So hang on to it and try it after. We're happy with the others can do after.
Oh, you can't. Oh, you're not so big. The first time I started and colors in terms of music, and after that, now she doesn't know us like much else. Now it's easy because I can't get the good sound.
Have some supplies on their 715s. They are providing some quotations, basic ones.
So what I would like to use because we have checklists, there's only one thing to recheck the whole line at full time. So they try to show it.
They will be at the same time. Same programs.
It's project.
Tech is between 180 to 420. We cannot measure it.
But okay, so if I so what can I so one thing that I made what would be
Yeah.
what you do with the something to the company something solid measurements.
Actually, maybe the stretchy and the cheap texture can be.
So
Can use the judgment eight school and like shells in the markets. You can get genetics for marshmallow or the gelables like that. The higher. Check the item compare.
at the master change that is some changes just expressing when I took this years I completely forgot that information. So completely forgot that.
Yeah. That gelatin works well actually.
So then what made
Different. Yeah. Directly. Area is huge. Actually, 2 weeks ago, I was in the Istanbul, the training center for the suppliers fair. Some suppliers. They have lots of actually that's knowledge. Best way to observe the supplier which produce they want to sell something to them. Their knowledge is quite efficient for you. Yeah, that's especially technical sales process. Very efficient.
So what I'm asking is, want to use samples of range of different potential
This is market is a market process. Get the temperature more than 100 degrees. It's hard to make it more. But just much more or less. Not more than 100 degrees.
So I'm just trying to see how we can see
Samples. Use mixer is very important. Since we need to make a space actually to get great challenge. Actually, yeah, I think first Jetson solutions. After that, the other ingredients gives the Jetson solutions. Providing relation temperature during the cooking is very hard. And then, actually, in production, I was in the cooking 6 months ago. There are different things. One is for cooking, one is for yes, but probably you need to use more gelatin in the foundation. If you have foundation is all already at the same time. Much less. That's the case. Yes. I'm just interested in production of that kind of stuff. Yeah. It's quite easy.
I just have to try to think what sales will
Washing is the gelatin.
which ones?
Fish gelatin.
So what about they produce the
I didn't see any products. It's that's it. But maybe this is some yes. Then also transparency. Differentiate types of gelatin. Since when I get into my house, actually, I can understand dating more of the. But the pectin ones can differentiate. Issues about that. But also they cannot trust the halal of gelatin.
I was watching where you are. I saw you briefly. Yeah. I was watching where you are. We have a lot of certificate issues at the department, so we couldn't attend. Oh, okay. Yeah, we're still maybe on the way. Yeah, wait. It looks a bit too cool. Oh, now I can see it. Oh, that's exciting. From the front, you can't even see it. It's like, you can't see it. Yeah. I can. Are you excited? Is it the first one? That's exciting. Do you have so tomorrow is tomorrow is last. Yeah. It's last day. Oh, so they used to. Oh, that's interesting. Take a bit of a break. When you're done. Oh, yeah, it stops tomorrow.
Nossa, tipo, eu tô apontando essa chega. Hocam ben sana anlatacağım. Ben yanlış çıkardım. Ulaşmıyor. Şöyle ikinci sayfa oldu. Şöyle iki sayfalara gidiyoruz. Ben çıkmaya yol tutuşum. Ben seni bilmem. Sen gün karıştır. Parmağın çarpma oldu. Beşi tıklamaya cesaret edemiyoruz ki. Şimdi bir daha acaba beşi görebilirsiniz.
But we can't buy from Amazon.
Then buy it once you're in the UK. Take it back.
Okay, so I can get fish. What would the blue be? Çok güzel olmuş.
Samples. Unpaid lazy schema kits. I want to in the middle of production. Yes.
We are magnet
Yes. It's the thing I can leave, let me fix that.
Efendim şarjı bitmez mi diyorum. Şarjı falan.
They're quite magnetic on the outside. They make a good fridge magnet.
Yeah, check some of these and then you can come back in 1 month and look at
Neden buraya gittik? Burada mı devam ediyoruz?
Yes, we can restart.
Lego. With your parts, some. Gotta get it.
Bak şöyle bunlar yapıştırılmış çocuk. Aynı şekil olanları yok. Bunu zaten. Şöyle aynı yönde olacak hepsi. Çünkü içinden bir şey geçirecek ya. Doğru olması lazım. Renkleri böyle birbirine şey yapacak. Ama eldiven al ve sadece şu noktalara koyun ki elinize dışında yapışmasın. Elinize bir şey olmasın.
Neyle mi? Çubukla mı? Yani
Evet,
çubukla.
Ayşe Sultan.
Şurada var aslında ya hocam. Çok kullanırız.
Bunu çağırıyorlar.
It is ours. I think.
Okay,
Yeah.
okay.
Yes.
We will start.
Yeah. You start and you take your place. Setting colors. I think it's by. Yeah, it has to be almost 30 minutes.
I was just trying.
Really?
And
You
then I
fixed
still,
it?
yeah, I did it again.
Okay, great. Arab said we need to go there. And he said other parts will be more complicated.
Okay.
Can you take this? Yeah, take it. Okay.
This is our.
No, it's not ours. This is ours.
Okay.
Burası
oldu
çok
ki?
sıcaktı. Oraya oturabilir miyim
Tabii ben
kalkıyorsan? Peki bu bir tanesinden 5 tane mi olması gerekiyor?
Tersten 5 tane
Aynen,
4'er.
tamam.
ikisinden de. Ama şunları yapacaksın sadece.
Hadi bunları mı
İçinde
yapacağız?
yok
Ha, tamam,
delik
okey.
olanları bunları yapmayacaksın sen.
Şurada.
Evet, orada.
Onları ben ayarlayayım. Sen onları ayarla.
Teknik olarak şöyle yapın. Şunu boyuyorsun üstüne yerleştiriyorsun tek tek.
Ben o zaman o renk senden, bu renk benden biliyorum. 5 tane, 5 tane gibi yapıyorduk değil mi? Bunu almam daha mantıklı. Zaten böyle yapmış. Evet. Evet, şuna taştı. Çok başka var mı? Şu önüne koymuştum sana. Ben çok fena düşünüyorum. İçini bırakma. Çok zor oldu.
Kolay gelsin.
Yapmayacağım.
Kamerayı şey yapıyorum ya.
Slide.
Goodness, this is really totally What's between? What's
It's a spacer. So they come shipped with spacers to make it easier. And then we keep taking the spacers out, but no, that's good. Yes. And that's, you see, you don't have a choice sometimes. Yes. Slide. Easy space to slide back to front, yeah. They are the fun times. Yeah.
Then in the bags of tomato. Pretty sure I've got some emails. So we can
Oh, look, there's some hands. No. Oh, look, there's paper there. Oh, there.
Yeah, it's already done. Comes through. Okay, so we have squares in the
Firmly in place. It might slide, but it'll be all right. Let's see.
So we have those so at the moment, we leave the whole in the middle. At the top and at the bottom, we will have the hole this way. They should all be one colour. One colour doesn't have to be top and bottom left and right. So bottom one.
Well, I'm going to take the two greens at the bottom of the pile. Yes, there's two places at the bottom. We're going to take one off. Okay.
So we'll leave that one, pop that in here. That's the truth. Okay, then in the corners, you need the other colour as well. And they should go this way. That's right.
The ones on the corner should be perpendicular to the other four centres.
When you have your grid scheme, you mark on the grid which side you want the roof to be. So you can line it up. So the So if you use the pen to mark on the box, and here, let me see the word. Oh yeah, so that would be in. What did you do? There are two sizes of glove. Should tell you which size is enough. So the white cup is medium, the red cups are large. That's two pieces of fish. Then three. Just makes it a little bit easier, and it will have not touching to the top. Possible to do without paper tile first and without paper. Quite stressful. And then you get to makes it easier to we're going to just look at in terms of practice.
Yeah, so between two magnets. Yes. Better pitch as well.
It's slightly less easy. The last one is the hardest magnet you've ever anything ever. But as long as you've got a good grip on the magnets and you're pushing the magnets, it should probably be okay. And the best thing you can do is every time you get one of these, you can shove on the top just to make sure all of them really well gets to the ground. And then you might see okay, and then the line on the top of the magnet should line up with the dots on the north to dots. And you might want to stick them, like stick them in to put magnets. So just slide on the magnets off. Yeah. So very good. Maybe you do that. And if you put one of those on. Let's go around.
One of you needs to play and one needs to put their words to it.
Hocalar aynı sıkıntı yaşıyor. Yes, you can see the
How is this? Magnets? Can we get this one?
Yes, it's
I'm going to question.
This is the last one.
Yani yanlış şey yapmıştım.
Yeah, the last one is
Yapıştırmayı ama gelmeden aynı işte. Bana da ver. Çekişmeden almış. Burada.
This is not one of my best.
Parçalanma da. Gözümüzdeki parçalanma.
Yes.
Sen 80 3 aşağıda, yukarıda 2 yan. Ben onu rastgele geldim. Ben de korkuyorum. We also did come back.
That's why I
Tamam kızlar. Sakin.
Bunun içinde dört üstü olacak şekilde benim işaretledim orada işte. O yüzden dedim.
Yine koyup iyice hepsini bastırıp spiralde sıkılaştıracaksın. Sonra şu ortadaki çıkartıp sonra böyle koyup yoksa dağılacak. Şöyle yap. Şöyle yap abi.
Uyuma ya. Görmek istiyorum. Yüzünüze sıçrarsa ne yapacağım? Benim yüzüme sıçrarsa. Sıçrarsa benimkine sıçrar. Bence evet.
Şuradan bir tanesi kaldı.
Kaç kere?
Bence 2-3 tane yapalım. Ama onu iyice sıkın. İyice sıkın. Sonra bir tane koymuş daha.
Şöyle biraz bir şey kaydetseydik. Aynen tam ortada.
Döndürelim mi? Döndürmeyiz ya. Bir tane daha takalım.
Çok güzel olmuş. Beğendim.
Sen daha yapalım. Sağlamalım.
Üç tane olsun.
Bak şu alttakini çıkart. Ama çıkartmasın ya. Neyse. Bir tane daha koy. Koy koy. Allah.
Alttaki güzel oldu.
Onu da o tarafa.
Yani eşitler. Başlıyor. Ben de çok iyi de.
Dersen çok hoşuma gitti lan ya. Bence bu okey ya. Ne olmuşsa bir daha yaparız artık. Yapacak bir şey var mı?
Hadi yapmışsın.
Şimdi ortadaki o alsın. Sağlam tutar zaten. Hangi tarafın o?
Şarkıların hepsini.
Nice. Take the bottom on. Then.
Yavaş yavaş gözleşmeye başladı. Böyle insana vereyim.
Böyle
Nasıl açtı?
Onu ben de dedim ya.
Biz
Zaten tamamladık. Ertan tamamladı. Ertan biz tamamladık ama şurası şey. Aynen.
Burada kaldırırsak bozulabilir.
Bir tane mıknatıs uzman çekebiliriz ama. Çok nasıl konu?
Kanka şimdi dolacak diye çok korkuyorum. Cam sağlamasın. Büyüye başlayalım. Biz çok seri yaptık bu işi. Devam edelim. Üç parçası var ya, iki parça geliyor ya.
İşte hepsini oturtmak lazım.
Bunun oturabilmesi için şey var mı? Konekte neredeydi?
Yok bakıyorum hala. Terslik var ya.
Şu köşeyi 5 tane uzun. Aşağıda yaparsak yapışmış olabilir. Oturuyorsun uğraşma böyle.
Kanka bunların düzgün hizada olmuş. Onları ilk bir bayağı konuklarla şeyi görmüşlerdi ya.
Ya.
Bak şu orada da. Bayağı çok.
Yapma yapma. Tamam çok. Orası çok güçlü değil. Olay güzel.
Hadi kız.
Olmadı.
They got a special. Before you talk on everyone's now broken at this stage because we thought that you should be able to push these out through the square. You cannot push these out through the square. They do not like it. No, they don't like it. They like it pretty badly. So you need to take this out and put the circle ones in before you put the top one. Yeah, I'm nervous. We'll get you another one. We'll get you another. I don't know why my finger is in there. But I'm happy about it. It's okay, right? Yes, you need to.
And I can do this as much as I want. Yok bakın hala şey. Keselim mi ya?
How are you getting?
He's so proud. You should be. That is not the
Hai problemi nella bandiera, queste switch per noi. So I started
Arkadaşlar böyle bir şey olamaz ya. Hayır, 10. dakikada yaptık.
sonra çıkartmanız gerekiyor. Bir buçuk saat onu çıkarıp tekrar bozup yapıyorduk. Hayır, yerine zaten bunu koyacakmışız. Yani birlikte bir şey koyacakmışız. Neden ilk başta onu koymak?
Hocam çekil.
That's why we are Chinese.
Sallamaya başladım.
Benim böyle dokunmuyor.
Sen anladın bana söyle. Sen anladın. Eren,